The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, ready for the least squares lecture 11. Homework is just being posted on the web. It'll be due, it's really to help you practice, get some experience on these sections for the first exam. That's Tuesday evening, so 8 days away. So the homework will be due the day after. So, and actually we'll try to move the review session to Monday next week, so you can ask me any questions about the homework or any review material. So, okay, so that's all a week away, and this week we get two great examples. Least squares is the one that comes today. But could I first, because I keep learning more and I've got your MATLAB homeworks to return, I keep sort of learning a little more from your MATLAB results. And I think because we spoke about it, it would be worth speaking just a little more. So if I'm going to take 10 minutes about this convection-diffusion equation in which I put in a coefficient d, a diffusivity, just to help get the units right. So this is your example, and it had d equal 1, of course. Okay. Well, first I realized that later in the book, I completely forgot that I discussed this problem. About page 509, I think. I discussed it a little bit, and just because it's worth, since we invested a little time, the little bit more will pay off. So first of all, the point is here we have convection competing with diffusion. And always there's some non-dimensional number. Here it's called the Peclet number. Actually, there's an accent on one of those E's. Peclet number, which measures the ratio, the importance of convection relative to diffusion. So it's V times a length scale in the problem divided by D. So then that has the same units as that. The result is dimensionless. Maybe you know the Reynolds number. This is very like the Reynolds number, which also measures in the Navier-Stokes equation the importance of convection, advection, and diffusion. And there, in that equation, the velocity v, that's a nonlinear equation. Navier-Stokes, it's tremendously important, and many codes to solve it, lots of discussion. Theory still not complete. In that problem, the v is u. It's nonlinear, and the term there that we took as a constant, as a given constant v, it's the same as u. So in the Reynolds number, this would be u, a typical velocity u, times a typical length scale, which would be like 1 in our 0 to 1 problem, divided by d, or mu, or nu, whatever number we use. Okay, so it's like the Reynolds number. And then it's turned out for this problem that people also use a number that gets called the cell Peclet number, where the length is taken to be as half the cell size, delta x over 2. Let me call that number p. So that's p. And what's my point? This equation is important enough to sort of see a little more about it than just the numbers that come out. So the MATLAB homework, which you did really well, did set up finite differences for this, right? And found the eigenvalues and solutions. Yeah, it's the eigenvalues I want to say a little more about. Okay, right? Because you set up a matrix K over delta x squared, and V times the center difference over delta x. And I guess I call that whole that combination L, and asked you about the eigenvalues of L. And you printed them out correctly. But there's more there than I think we have understood. And I want to make some more comments about that, because it's quite important. And the comments are clearest if I just reduce to n equal 2. So that matrix, well, the off-diagonal part of that matrix had some number b and some number c. Actually, we could figure out what was the b in this. This produced a -1, 2, -1, right? So part of the b was the -1 over delta x squared. And then from this was a plus v and a 1 over, well, it's a center difference, so I should divide by 2 delta x. Is that right? Is that what a typical off-diagonal thing that in the matrix that you displayed? That's what's coming from the off-diagonal of k, and this is what's coming from the center difference c. And then what would this c thing be? Well, the c is below the diagonal, so it's also that -1 over delta x squared. But now this is a difference, so it's going to be a minus, right? I think those would have been your entries for b and c. Okay, so can we just think first? What are the eigenvalues of that matrix? It's a 2 by 2 simple problem. The trace is 0 plus 0, so that the eigenvalues will be a plus-minus pair because they have to add to 0. And I think that's the plus-minus pair you get. Let's just check. What's our other check? They will add to 0, the plus the square root and minus the square root, and the product of the two eigenvalues, lambda 1 times lambda 2, will be, we have one of them is plus, one with a minus, so it would be minus bc. And that's correctly the determinant. So it's good. These are the correct eigenvalues. Okay, now, let me ask you about the signs of b and c. If b and c have the same signs, like maybe even equal, 1, 1, what are the eigenvalues? So in that symmetric case, if b and c are equal, the eigenvalues are right here. If b and c are equal, say equal to 1, the eigenvalues are plus and minus 1. But what if the signs are opposite? Everything changes. What if b is 1 and c is minus 1? That matrix would then be a 90-degree rotation. It would be anti-symmetric if b was 1 and c was minus 1. And our formula is still correct, but what does it give us? If b is 1 and c is minus 1, this is what have I got here? I've got I. So the eigenvalues change from plus and minus 1 in the symmetric case to plus and minus I in the anti-symmetric case. And I think that's what you guys saw at a certain level of v. Or I hope you did, because that was the point about eigenvalues. Now you may say, what about the diagonal? Well, I claim diagonal is very simple. What's the diagonal? Let me just change to add some. Now I'm going to allow myself a diagonal, and I'm just going to change. What happens if I have A and A, same entry on the diagonal? What are the eigenvalues now? You know, this is just like a great chance to do some basic eigenvalue stuff. What are the eigenvalues of that matrix? Well, I've added A times the identity. I've just shifted that matrix by A. So the eigenvalues all shift by A. So the eigenvalues are now A plus and minus. So no big deal. But so you see that the A is actually not important, not the key to this question of are they real or do they go complex? They're real. So the eigenvalues of this are real when B and C have the same sign. If B and C have the same sign, I have a square root, no problem. When B and C have opposite sign, what do I get? When B and C have opposite sign, I'm taking the square root of a negative number and I've gone complex. Do you see that the change from real eigenvalues, which gives a nice curve, to complex eigenvalues, which gives a very bumpy curve for the solution, is just happens when, like for example, B. So is it B that's going to go to 0 maybe, and then beyond that? So this sign is well, this sign is for sure negative, right? So C is staying negative. And originally, for a little delta x, B is also negative. Yeah, yeah. What's happening here? I think, yep. I think this looks okay. So I think that the transition that you, I hope, observed comes when B hits 0. When the combination of V and delta x is such that at B equals 0, we switch from real eigenvalues to complex eigenvalues. Okay. And when is B equals 0? Well, that's when this negative guy off the diagonal it just exactly cancels this one. So B is 0 when what? So if this equals this, 1 over delta x squared is equal to V over 2 delta x. Let me multiply both sides by delta x squared so that I have a nice 1 there. Multiplying by delta x squared, we'll put a delta x up here. And what have we discovered? This is why I wanted you to see it. That the transition comes when the Peclet number is 1. So that Peclet number, that cell Peclet number, is exactly the point that we observed of transition from real eigenvalues to complex eigenvalues. And that's the transition. So it's that combination. This is the Peclet number, cell Peclet number. It's that combination, P cell maybe. Yeah, so this is like just, we've done the computations and now we gradually get back to the meaning. And I just wanted to take this step back to the meaning to see when do those numbers start going complex. You may have noticed or you may not have noticed that it'll happen when one of those, when that upper diagonal changes sign. Now you could say, okay, that's the eigenvalues. What's the consequences for the shape of the solution? Well, I haven't figured all that out. I'd be happy to have some more thoughts about that. But what you noticed, I think, in the computations is when, if V got too big, so that that P was bigger than 1, if V got too big, so convection was dominating and our delta x was not small enough to deal with it, you should have seen the points on the discrete values were oscillating instead of a proper smooth. I mean, the proper, with a large V, the correct solution, I think, goes, there's practically nothing for here, and then it goes, this is a really large V. Take V equal to 1,000 or something. It climbs up like mad. Here's the halfway point where the load is. And then it goes along here, and then it climbs down like mad to satisfy the boundary condition. I didn't know that that's what would happen for large V. Okay, what I'm saying is, and undoubtedly it could be understood physically, So I guess what I'm saying is there's just more good stuff in any computation than purely the numbers. And this is part of the good stuff in that example. Okay, I hope you liked that. Because, I mean, here you did the work, but then to understand it is frankly still underway. More thinking to do. Okay, so that's back to least squares. Okay, here's today's lecture. So remember where we started last time. AU equal B. Last time I wrote F. I regret it terribly. I can't fix it, but it's B. I want B there to be the right-hand side. Okay. And I jumped to the equation that determines the best U. There's no exact U because we've got too many equations. Right, you remember the setup. We have too many equations. There's noise in the measurements, and we can't get the error down to 0. There's some error. And the best U was given by that equation, and we want to say why and understand it from two or three ways: calculus, geometry, everything. Can I first, because I love my little framework here, fit it in, because it's quite important that this example and then others fit in. So U is our unknown, as always. Then the matrix A in the problem produces an AU. Now, two things to notice about E, which that's the same letter I used for elongation. Here it's standing for error. Two things to notice. One is that the source term, which is B, comes in at this point of the framework. When we had external forces on springs and on masses, it came in at this point. We had an F there. Now, so that's why I'd like to keep those two separate. The B's are like voltage sources. They come in here. The F's will be like current sources. They'll come in there. Oh, it's beautiful. Yeah. Okay, one more thing to notice. A is coming with a minus sign. In mechanics, in masses and springs, we had E equal AU. Here, it's natural to work with the error or the residual B minus AU. And that minus sign is natural in physics and in electrical engineering and hydraulics. Flow, where's that minus sign coming from in flow? Well, flow goes from the higher point to the lower, higher voltage to the lower voltage. And that usually produces that minus sign. No big deal, of course. Okay. Now, so that step is fine with the framework. What do we expect in this? What do we expect in that middle step? So what's our name for the matrix that goes there? Everybody's got to know this framework. C, right? Only I've been taking unweighted least squares. So for unweighted least squares, C will be the identity. And C doesn't show in our equations. So C is the identity when there are no weights, when all the equations are equally reliable. And that's pretty common, of course. But not always. And we'll think, okay, there is a weighting. So W which is CE, is weighted errors, you could say. So the letter W comes up appropriately again. Weighted errors, and then what's the good weighting? May I stay with C equal the identity for the moment? Unweighted least squares, because that's by far the most common. And then W and E are the same. C is the identity. And finally, there's the last step in our framework where we always expect to see a transpose. And we do, and we have to say why. So that's where I left it last time. That this was the picture. This is the equation. If I had a matrix C, it would go there and there, right? Because I'd have B minus AU, and then I'd apply C before A transpose. So C would slip in there before A transpose on both sides. So that would, with the C's there, that would be the weighted least squares equation. You see that it would be A transpose CA instead of A transpose A, but still the main facts are there. Okay, so where does the equation come from? All right. So one source, one way to get the equation is from calculus, from minimizing. Set a derivative to 0, calculus. And what's the quantity we're minimizing? We're minimizing that squared error, because this is least squares. We're minimizing this, E transpose E, the length of E squared, the sum of the squares of the errors, which is B minus AU transpose, B minus AU. Again, I could say where to slip in the C matrix. If there was one, it would go in there. C would go in there. C would go in there. There'd be a C in the equation. But let's keep C to be the identity. Okay, so I minimize. It's a quadratic. It's got U's times U's, so second degree. And what's the coefficient in that second degree part? Well, the second degree part is coming from AU transpose AU, from this, right? This times this is going to be linear. This times this is going to be linear. That times that is just going to be a constant. Its derivative is 0. But this times this is altogether, that times that is the U transpose A transpose AU, right? So that's the quadratic part. And my only point is, it's like our old, it's like our stiffness matrix. We're seeing the matrix in here is A transpose A. In other words, when I do calculus, and maybe I'd prefer to see something than just compute away, take derivatives mechanically. So I'm going to leave that which is done in the text, the setting, finding the derivative, setting to 0, and what does it give? It gives us our equation. Okay, so that equation will come when I set the derivatives of this thing to 0. So that's one totally okay approach, but I like to see a picture with it. Okay, so I hope that's all right. To take the second approach is to see why. Why is A transpose W equals 0? Why is that? What's going on in that key step? This is always the key step. This is like the setup step. This is the weighting step with constants coming in. And here's the key step. Okay, so let's see that. All right, so my picture. All right, let me draw that picture again. Okay, my picture is that, and I had my example had, was in 3 dimensions. So M equal 3. I've got 3 equations. The matrix A, I'm afraid I don't remember what it was, but I think it was something like 1, 1, 1, 0, 1, 3. Was that maybe it? Just to connect to last time. And what I'm now calling B was the vector 1, 2, 3, was it? Or was it not? It was 0, 1, 2, maybe? That's right? Okay. And what was the point? If I draw the vector B, it goes there somewhere, B. If I draw the first column of A, it goes here somewhere. If I draw the second column of A, it goes there somewhere. And if I draw all combinations of these columns, all combinations of that vector and that vector, what do I get? I get a plane. I get a plane. There it is. That's a plane. That's the plane. This is from column 1. Here's column 2. This plane is the column plane, or column space. It's the column space of A, because it comes from the columns of A. Now, what's the point about this plane? The point is that if B is on the plane, then I'm golden. If B is on the plane, then B is a combination of the columns. That's what the plane is. And I have a solution to AU equal B. So B on the plane means AU equal B is solvable. And it could happen, of course, like perfect measurements. But we can't expect it. When we have 3 measurements or 100 measurements or 10,000 measurements, we can't expect perfection. So usually B will be off the plane. Okay, now what? What happens when B is off the plane? Let me just complete that picture and you know what's coming. If we're going to get, AU or AU hat is going to be on the plane, so I'm looking for the best U hat. I'm looking for, can I just erase this to make space for what you know I'm going to draw? Here are these little columns. Let me put them there. Okay, what am I going to draw? The projection. The projection. I'm going to draw, what's the projection? The projection is the nearest point that is in the plane to the B that's not in the plane. So here's the projection P, I drop down this thing. There's the projection P, little p. That's the projection of B onto the plane. I think your mind says, yeah, that's the right choice. And you want to tell me what this is? That is the part that we can't deal with, the part we can't improve. We've made it as small as we could, and it's E. That's the error E, and this P is the best guy that is in the plane. Do you see that this is the picture? You get an actual picture of what's going on. You're splitting B, the measurements, into the part you can deal with, the projection, the AU hat that is in the column space. It is a combination of the columns. Those points do lie on a line if I'm doing straight line fitting. And the part that you can't deal with, the E, the difference, B minus AU, which is not in the plane. And now I'm still looking for the equations, right? I've just named some stuff, but I haven't got an equation for that projection. And so what's the key fact? What's the key fact in this picture that's going to lead me to an equation for P and E and U hat and everything? The key fact is that dotted line is perpendicular to the plane. If I'm looking for the closest point, everybody knows that's what projection involves. Go perpendicular. This is a right angle. That E is perpendicular to the whole plane. Not only perpendicular to P, it's perpendicular to everybody in that plane, right? I'm dropping the perpendicular to the plane. Do you accept that? Because if you do, we're through. We just write down the equations for perpendicular, and we've got what we want from the picture instead of from a calculation. Okay, so what's the idea? So E is perpendicular to the first column. So B is not, B in the plane, we would be golden. Let's suppose we're not in the plane. So now we have this 90-degree angle, this perpendicular projection. And I want to say that it tells me that the first column, I better name the columns. Can I just call this column A1? That first column is A1, and the second column is A2. So those two columns, whatever they are the guys whose combinations give us the plane. And it's the plane that we're projecting onto. It's the plane of all combinations that comes up here. Okay, so what's this 90-degree angle? It says that A1 is perpendicular to P, right? No, sorry. Say that right for me. The first equation says that A1 and what are perpendicular? E, thank you, E. So the first equation says that A1 transpose E is 0. And the second equation says that A2 transpose E is 0. Those are my two equations. Okay, I have to convert those now into matrix language because those are, I've done them two separate vector language. I want to get into matrix language, but it's easy to do. Here I have, look, if I have two equations, let's get a matrix here. This is saying, this is the same thing as saying, oh, what's it saying? What A1 transpose and A2 transpose, what are those? They're the rows of A transpose. So the matrix way to say that is A transpose E equals 0. In other words, this is saying both at once, right? The first row of A transpose times E gives 0. The second row of A transpose times E is 0. So it's A transpose E equals 0, which is what we wanted in this case where W and E are the same, because C is the identity. Okay, and let's just go one step further and see. That's A transpose B minus A U hat is 0. Remember, this 0 stands for 0, 0, right? That I wanted to put the two equations together, so I've got two components on the right-hand side. And then I just plugged in what B is, and now everybody sees it, right? Everybody sees that we've got the picture. This 90-degree angle was the key to these equations, right? Because if I put A transpose A U hat onto the other side, I've got exactly the normal equations that I wanted. Okay, and you know, we're taking the time to see the picture and the form of the equations. Then I can plug in the numbers, but the thinking is where the equations come from. Okay, so that we're there. All right. Now, what to do next? Now we've understood where the equations come from. I didn't go through the steps of taking the derivatives, but that would work. Or this picture. I love this picture. Let me stay with that a little bit longer. What is U hat? Can I just go over here to say, okay, what have we got here? We started with AU equal B, so, and then we got the projection was A U hat. But now what is U hat? I'm just going to just assemble things here. U hat, we figured out by the 90-degree angle, comes from this equation, which is that equation, which is A transpose A U hat equal A transpose B, the central equation. Okay, that's the central equation. Okay, now tell me what plug in U hat here so I get a formula for the projection. While we're doing all this stuff, we might just as well put those two pieces together and have a formula for the projection. So it's A times U hat. I hope you like this formula. It's kind of goofy looking, but you'll remember it. Okay, what is U hat? The whole point is that this matrix is good. It's square, it's symmetric, it's invertible. We'll have another word about that. And now I'll invert it times A transpose B. That's the That's the goofy formula that I wanted you to see. The projection of a vector B onto these columns of A comes from applying this matrix. You could say, like, sometimes I call it the matrix of 4 A's. Now, it's worth looking at that matrix. Often I'll call that matrix capital P. It's the projection matrix. You give me any vector B, I multiply it by this matrix, and I get the projection. Okay, it's just worth seeing what this matrix P, these 4 A's, is. What are projection matrices like? Okay, now first of all, when I have an inverse of a product, any reasonable person would say, okay, split that into A inverse times A transpose inverse and simplify the whole thing, and what will happen? It's not going to be legal, but let's just pretend. If I split this into A inverse times A transpose inverse and simplify, what do I get for P? Do you see it? I'll get A, and if I try to split this into that, what do I have here? I've got the identity. That's the identity. That's the identity. The result is the identity. That doesn't look good, right? P is not the same as B. This matrix cannot be split into these two pieces. A is rectangular. That's its problem. So this is, if A was square, oh yeah, think about the case when A is square. Suppose M equals N. That case will be included here. If M equals N and my matrix is square and invertible and golden, then all this works. The projection is the identity matrix. And what's with my picture? What's my picture look like in the case where A is a square matrix? Give it another column. Fit this thing by a quadratic. So that if I was fitting instead of by a straight line by a quadratic, it turns out I'd have 0 squared, 1 squared, and 3 squared in that column. I'd have a 3 by 3 matrix. It comes out to be invertible. Now what's going on? Now what's my problem? AU equal B. Now suddenly M is still 3, but now N is 3. What B is? And what happened to the plane? B is in there, and now what's there? It's now the combinations of what? Why did that plane come in? That was the combinations of 2 columns, but now I've got 3. The combinations of 3 columns, those 3 columns of an invertible matrix is what? Are you with me? The columns, if I have a 3 by 3 invertible matrix, these 3 columns independent, pointing off different directions, not in a plane, then when I take the combinations, I get R3. I get the whole space. I get everybody. Every vector, including this B, and any other B you want to suggest, will be a combination of these 3 guys. So what's my picture here? My picture is that plane grew to be the whole space. So what's the projection of B onto the whole space? B itself. And what's the error? 0. Good. Yeah, so that's the nice case. That's the standard case that we've thought about in the past, when M equaled N. Okay, and in that case, P is the identity, and that'd be all true, but normally it's not. Now, so I want to come back to this P just to mention an important fact about P. And it comes again from the picture. So this is a projection. This is what I'm calling the projection matrix. It's the matrix that does the projection, and there it is, 4 A's in a row that multiplies B. Now, here's my little question. Linear algebra is just full of these different kinds of matrices. rotations, reflections, symmetric matrices, Markov matrices. It's just every problem has matrices. Now here we have a projection matrix. Now what I want to know is, what happens if I project again? If I take the vector b, any vector b, I project it, and then I project again. So project twice and just tell me, you know what will happen. Suppose I'm back to this picture. I project b to p, and now I project again. Where do I go? Same place, right? Once I'm in the plane, the projection stays right where it is. So what does that tell me? That tells me that p squared on b is the same as p on b. P squared is, if I project twice, no change. It's the same as projecting once. So the projection matrix has the property that p squared is p. And actually, we should be able to see it if I write out this whole miserable thing twice. So now I'm going to be up to 8 A's. Sorry about this, but I promise not to do p cubed. Okay, A times A transpose A inverse times A transpose, that's 1p. I'll write it again. There's the second p, so that's p squared. Do you see anything good there? You see in here A transpose A, that combination, and that combination there. This cancels that to give the identity, and what am I left with? I'm left with A, the inverse, times A transpose, which was exactly P. The algebra is just coming along with the understanding that we know. Okay, so that's the projection matrix. So this is the theory of projections in a nutshell. In a nutshell. This is projections onto the column space of A. Now, I have to remind you about one little math point. Not so little, I guess. How could I say little for math? Right. Okay. Is A transpose A invertible? We're plowing along as if it is. That's going to be our assumption. But what's the condition for A transpose A to be invertible, and which allows all this to work? When is A transpose A invertible? Okay. So this is like what I'm doing here now is I'm separating the positive definite one. When A transpose A is positive definite, the good normal case, when all our equations work, from the semi-definite one, where we overlooked the fact that A transpose A, where somehow the experiment wasn't well set up, we got an A transpose A that is singular, and just to see when could that happen. Okay, let me just remind you. I wish I could. Oh, this is important. Why don't I give it some space? It's really straightforward. Let me just go through those steps again. So, if it's not invertible, if some A transpose A U is 0, this is always the risk that we have to check out and be sure we don't have and understand. So if A transpose A U is 0, then that would lead us, I could multiply both sides by U transpose 0, right? Safe. Multiply whatever that U might be, multiply both sides by U transpose. But what is U transpose 0? 0, nothing there. Okay. Now what? Now how do I understand this guy? Well, you remember the key. Everybody remembers the key. You look at that thing and you say, hey, if I put in parentheses in the right place, that's the length of AU squared. So that's the small trick that is multiplying by U transpose and then seeing what you've got that we've done, and you should know it. And now if the length squared is 0, what does that tell me about AU? If I have a vector here whose length is 0, that vector must be 0. 0 vector is the only one for which the sum of the squares will give 0. Okay. And if AU is 0, I could multiply both sides by A transpose and complete the loop. Actually, I thought of that when I was swimming this morning, that line. Just to see once again, when it's sort of interesting then. A transpose AU equals 0, which is the bad thing we hope we don't deal with. And when does it happen? It happens when AU is 0. Yeah. So, so our assumption always has to be this, that there aren't any U's, except the 0 vector, of course. That's always going to happen. But we always have to assume that AU is never 0. So we have to avoid this. So to avoid that, assume A has, this is the key word, independent columns. Since this is a combination of the columns, independent columns means what? It means that the only combination of the columns to give 0 is the 0 combination. So did I have independent columns over here? I sure did. That column and that column were off in different directions. They were independent, and that's why I knew we were fine. A transpose A was 0. I would have to really struggle to find, well, I'd have to think a bit to find an example where we run into trouble. Yeah, these squares, well, I certainly could in many applications, but the straightforward applications of fitting a straight line, A is going to be a column vector of 1s and a column vector of times, and those are different directions, and no problem. Okay, so that's A transpose A. Okay, what else to do with this topic? Because there's a whole world of estimation. I mean, statistics is looking over our shoulder, I guess. Really, we should realize that a statistician is saying, yeah, I know that, but, and then going on. And what is that guy, what more does he have to say? Okay, so you've got the central ideas. I guess the statistician comes in this is where, that's the statistical constant now. That's the constant where, and what do statisticians compute? They say you've got errors, right? And of course, in any particular case, we don't know what that error is. Otherwise, we could take it out and we'd get exact solution. We don't know what the error is. What is reasonable to know about errors? Okay, we're doing a little statistics here. What we want to know, somehow that error, that particular error of the experiment that we happen to run, and if we ran it again, we'd get a different error. Those errors come out of some sort of error population, like dark matter or something, right? Just like a bunch of errors are out there, noise. And what could we reasonably assume that we know about the noise? We could assume that its average is 0, mean 0. So statisticians always, that just resets the meter, right? If you had a meter that was or a clock that was always 3 minutes ahead, like this one, you would reset it. And we'll do that one day. Okay, so you'd reset to get the average 0. Okay. But that doesn't mean every error is 0, right? That just means the average error is 0. So what's the other number? what's the other number that statisticians live on? It's the deviation or its square, which is called the variance. Right, variance. So that's the thing that you could assume that the errors have mean zero and have some variance. You could suppose that you knew something about the variance. You don't know the individual errors, but you know whether the errors are like on a are very small or close to zero, or a large. So this is a small variance. So 1 over sigma is sort of that distance, 1 over sigma. Here, this is a large variance where we, the error, the magnitude of the error could be much larger from this. So those are the two numbers. Mean zero, that leaves us just one number, and the variance, the standard deviation sigma, or the variance sigma squared. Okay, one moment on these squares. Okay. Well, let me just say what the weighting matrix would be. And then I can tell you in a moment why. And what would the weighting matrix be if our three equations, that came from one measurement, and this came from a second measurement, and this came from a third measurement, if they came from different meter readers with different variances, suppose then the right C matrix will be a diagonal matrix, beautiful, and what sits up there, what sits there, what sits there? We don't have spring constants anymore. We have statistics constants. And what's the number that goes there? It's that one is the third guy. So it's associated with the third measurement. It's 1 over sigma 3 squared. Those are the numbers that go on the diagonal, the inverses of the variances. And just to see that makes sense, if that number is unreliable, if it has a large variance, then I want to give it little weight, right? And if this third meter is very unreliable, I'm not going to throw it out entirely, but I know that its variance is large, and therefore I'll weight that equation only a little with a small weight. Suppose sigma 2, so this guy is 1 over sigma 2 squared. Suppose this is an extremely reliable meter. That measurement has little expected error. Then I want to weight it heavily. So it has a small sigma 2, and that gives it a large weight. So those are and sigma 1 similarly. So that's the weighting for the case that you can actually hope to use in practice. I'll just mention that statisticians would also say, wait a minute, measurement 2 and measurement 3 might be interconnected. They might not be independent. There might be a covariance. And then that gets them into more great linear algebra, actually. But if I want a diagonal matrix C, that's the case when my measurements are independent. And basically, I'm whitening the system. I'm making the system white, making it all equal variances by rescaling, by weighting the equations. Okay, thanks. Wednesday is the next big example of the framework with B and F. See you then.